Good morning, everyone. Welcome to another episode of Xah Show. Today is July 15th, 2019, Monday, 3 o'clock, 3:20 p.m. San Francisco time. And today we are going to talk about math, mostly mathematics. I forget about that. I was late for 20 minutes or something. Okay, so let's talk about mathematics. Some interesting things. Uh, okay, so yeah, okay, I'm gonna show you some interesting things about math. It's Bach music. Close it. So so let me show you some of the. I want you. I'm waiting for people to come on. One people is here. Great, fantastic. Yeah, God, just closed that by mistake. One people is here. Say hi. We are going to today's topic is math stuff. I'm just going to talk about math stuff. Wait, why does it say offline? What's going on? Oh, live. Okay. Um, Today's topic math. Okay, so let's begin talking about it. Math then, mathematics. So let's go to my math blog, and let me show you. Let's see, where do we begin? Okay, let's just begin with that. So I have this page you can go to. This is a collection of wonderful math software, free. They are online, and you can sometimes are there for Windows, some are for Mac, and just you go to my math blog like Sali Math, you'll find it. So this is math software. This is my collection of math software. Collection of them that I started to do this since 1997. So many of these are great, fantastic software. You can plot surfaces. This is differential geometry. This is very advanced. And you have contour. Um, these are called contour iso iso something surface. Anyway, usually it's called contour plot. Okay, and then you can differential geometry again. Um, so collection of math software and great ones. And this one is spectacular. You really should try curved space. It shows you it visually. All these are visual geometry software. Visual meaning it's fun. You don't have to, like, when you try these softwares. Some of them are really advanced. For example, this one is about ciphered surface. I don't understand it, but it has to do with, I think, topology and knot theory. Cipher surfaces. So this, for example, this topic is very advanced. You have to. It's kind of graduate math, but most of these software, and this too is like graduate math. This one is talking about curved space, like four manifold, three manifold, yeah, curved space, things like that. Anyway, they, the math subject of some of these software may be very advanced, but however, the software is fun to use. Like, you don't have to, like, when you try this, you don't have to, like, oh, I need to learn some math. No, you can just play with it. This one lets you fly through space, in a typical, like, three-dimensional space we live in. We perceive it as Euclidean space, so-called Euclidean space. It's like a flat 3D space, three-dimensional space, flat. But this software shows you three-dimensional space that are not flat. So what do you mean a space is not flat? It's that's the very interesting thing about math. That's why math is intriguing. You see, when you have a line, if you have a line or if you have a surface, like let me show you. Like for example, I have a paper here, and that's a surface, flat. Now, if I can bend it, or if I can have a cloth, like this is a surface, like a flag or a tower, they can bend they can be bent. But all these surfaces are two-dimensional. You can see they are just two-dimensional, even though they can bend, but they are still two-dimensional. But you see, okay, two-dimensional surfaces. There's something interesting. For example, this piece of paper, I can bend it, and I can, let's say, I can bend it like into a row, like a joint, a cigarette joint or a pot joint. You see, now it becomes a cylinder. And now it was a flat surface. Now it's a cylinder. Now, but if you imagine, if you are ant crawling on the surface, if you go straight, you will come back to where you began. Now that's an interesting thing. That's an interesting property. You can observe that on a piece of paper, a two-dimensional space. You can easily observe it because we are from a three-dimensional space. Now you can see there's a concept of flat versus curved. When it's curved, you might have this very interesting property where you go straight, in a direction, but you will end up, coming back to where you begin. That's an interesting property. That does not happen when you have a flat, space, 2D space. So that's very interesting. Now, if you go in three-dimensional, there's similar things happening because you see we are in three-dimensional. We cannot see it, like meaning that we cannot see the whole three-dimensional space. But just like the flat two-dimensional space, three-dimensional space can also be bent. They can be bent in quite a few ways. For example, one of the way a two-dimensional space bent is, for example, you can bend it into a cylinder. Another example is a sphere. You see, a sphere is also a ball. It's also a two-dimensional space, but it's curved. It's bent. So that imagine if you live on Earth, for example, Earth, you go all the way straight, you will actually end up, at the position where you began. You see, and in fact, doesn't matter what direction you go, doesn't matter, east, west, or what direction you go. If you keep going straight, straight, and you will end up at, the place you began. So that's an interesting thing about that's a about a two-dimensional space. So this is an example of curved two-dimensional space. And as we mentioned, another example of curved two-dimensional space is like a cylinder. But now notice they have different properties. On both a sphere or a cylinder, you can go straight and arrive at where you began. But however, on a sphere, it's such that you can go in any direction. You will always come back at where you began. But not so for the case of a cylinder. On a cylinder, there is only one direction, like up or one direction, like a straight line, that way or that way. That you will, if you go straight, you will come back to where you began. So even though both of these curved two-dimensional space has this special property where you can actually go straight and come back to where you began, but on a sphere you have it's kind of this property applies to any direction. So we have just explained, a two-dimensional curved space, and some interesting properties that does not happen with a flat 2D space. Now, so far we are all talking about two-dimensional. Now, so the interesting thing is when you go into 3D, even though we cannot see it, but if you do the math, you can easily see it that in 3D the space can also be curved. So that is to say, imagine you have a rocket. We shoot. NASA should fly rocket to space. If you shoot a rocket and the rocket goes straight, does not turn, it just goes straight. It is conceivable. It is. It may be the case that it keeps going straight, it will actually come back to where you begin, come back to Earth, even though you are going straight. If the three-dimensional space is a curved space. So exactly what how does it curve? That is the math. That is how you want to study. That's you study differential geometry and topology. These are the relevant math branches you go study. So this application is called curve space, and there are many different great softwares for geometry math. So this one, for example, it does phase plot, very very fantastic. Let me show you phase plot. Most of all these software are most of them are interactive, so it's very fun to use. You see, this is fantastic. Let me show you. So you move your mouse anywhere, then you can shrink. You can see the whole thing. You see, this is a phase plot. Now I'm not sure exactly what is phase plot, but you can if you know complex numbers, it's not difficult. You can at least you can understand what a phase plot is. This is phase plot. You can start to read Wikipedia. So it's all these are beautiful, fantastic math software I've collected, and this one is also interesting. So many of them. There you got fractals. So check it out. Many great factor software. So good morning, cat 42, 44, 44, not 42. So okay. I got 3 people watching. So let me read the comments. Cat 44 says, "Have you tried any of the fractal software around?" Yeah, of course. 3D Mandelbrot, Apophysis, yeah. I've been trying. In fact, I've been a bit. I have been obsessively trying all fractal software that exists out there that you can find since 1990, since 1997. So that is why I have this collection of software, and this has been 20 years since 20 years ago. So 20 years, things come and go. I start to have this page in 1997. Then after 10 years, after 20 years, you can see you get old, and you can see the society changes. Like some of the software author you check, some of them, they are long time outdated. And in fact, I have another page, old math software. Let me show you. Okay, so this page is a bunch of software that's no longer there. The people get old. It's 20 years. People get old. Some of them, maybe some of them still update their software. Most of them gone. For example, this Java written in Java, they are dead. All these, lots of them. So it's like 20. It's like history. You see the history of the software. So anyway, these so fractal software. In fact, so I started to do this 20 years ago. In fact, today, I haven't spent much time on check out where because today actually there are quite a lot. I think I don't have time to maintain, like go into detail and keep collecting what's the best fractal software, but I did that anyway. So that's great math software. So let me talk about some other math stuff. Okay, so math stuff, and let's go to math. Let's go to math blog. Okay, great math software, a course in universal algebra. Now, universal algebra is now this is very advanced. This is like a graduate. I don't know universal algebra, but I'm learning it. So if you are interested, it's a textbook. It's a free textbook by these. I think they are professors. So uh, universal algebra. So what is universal algebra? It's basically it's like you have group theory, ring theory, you have field theory, you have abstract algebra. Algebra theory. In algebra theory, you try to study all these algebra. Field, ring, vector space, all these in one coherent setting. So you and also you study them using kind of equation instead of the equation, using operators instead of you try to eliminate things like there exist, the condition, the axiom, there exists an element, identity element, such that, so on. You remove such axiom, because when you do programming, those kind of thing like there exist, they are not computable. They are so anyway, I don't know very much about this. I'm learning it. So this is universal algebra. You study, ring, groups, vectors, all these algebraic structures in a coherent context. So in a more generalized context. And if you are into category theory or proof systems, they are related. So that's a textbook on universal algebra. So let's see the next topic. Yeah, let me show you three books that's very interesting, math books. These three books are fantastic for beginners, programmers, if you are a programmer. So one of them is graph theory. This is a great, the fantastic, most wonderful introduction to graph theory. You do not need any prerequisite. You don't need calculus or anything. You can, graph theory is very much applied math, especially for programming. So I read this in 1990s, 1990 something, 1995 or something, and you can buy on Amazon. It's very cheap. Uh, let's see how much. $5. It used. This. Anyway, $5, $6, paperback. You can also learn graph theory from Wikipedia. Wikipedia is very rich. You can learn it, but sometimes, but if you are new, if you are a beginner, if you don't any, you don't have, if you don't have math background, and you try to read Wikipedia, usually you get confused because Wikipedia has lots of things. They have some of them are graduate level, some of them are research level, but they are all together under graph theory article, because they are properly under the graph theory title. But then, so that's, so books sometimes is very good for that. So this book I highly recommend, graph theory. You don't need background. And also this book, groups and their graphs, I recommend. Just go to Xah Math blog, you'll find it. And the edition I read is this one. This book is also very old, 1964 originally. So if you this edition you buy on Amazon, it's like $10. Yeah, $10 used. Um, but there's a newer edition. Typically these newer editions, they don't do much. Okay, so if you can get it with a cheap edition, that's totally fine. The newer edition is like $25, and they don't add much actually. They change the writing style a little bit. They and usually it's marketing stuff. In fact, if you want to study calculus, any calculus textbook from 1990s, 20 years ago, or 30 years ago, will do perfectly fine. Just go to a used bookstore, $2, get those 20, 30 years ago calculus textbook. Instead of otherwise today, you go buy a math textbook, calculus textbook, that's like $200, $300. Yeah, yeah, it's extremely expensive. And why is that? Because it's almost like a scam and collusion between the professors, American education system, like this calculus textbooks steward, this one is $250. Latest edition back in 1991. I wasn't using, well, 1991 there's also this book. uh, Back then it's $90, and now it's $250. And if you look at the content, the math content do not change at all. They just add, they pump out editions because to prevent people from using old books, using prevent people, they can resell and all that. Good morning, Danielle. So this article explains why textbooks are expensive. In a nutshell, is that if you sell a textbook, you write it once, you sell it. After you sell it, nobody will buy it anymore because the books are out there. Once student graduate, they throw it away. They sell it back to bookstores, old bookstore, so then people can buy the old edition. So you don't make money anymore. So these publishers or authors, they need to create a new edition out of the blue. So what they do, even if there's no need to change, so what they do, they try to change a little wording, change the exercise. They do that artificially, just so that you have a new edition. Then the professor will require the new edition, so that your old edition, you cannot use the old edition from bookstore, from old bookstore. So that is the way they artificially control. You always have to buy the new edition, and for most people you don't know, like, oh, this is new edition, that edition is 3 years old, oh, I must get this new edition. You don't know. But actually the math content, they actually do not change in the past 30 years or even longer, especially for beginning calculus at least. So when you buy math textbooks, you can remember, you can get the old copy. So math textbooks. So I'm talking about group theory. So this is a great book on group theory. Group theory is what is the most fundamental math part of math. So this is a thin book. Spend I would say, if you really try to study in detail, you can finish this book in a week. 2 hours a day. Read it in 3 days, in 4 days. Then you will know the real, the hard group theory, which is fundamental. It's even more fundamental than graph theory. Okay, graph theory. You see, I'm about to digress. You see, when we talk about the math curriculum, what courses, what, first of all, what subject, what kind of branches are there in math? That's one thing. Then, what do university teach? What exactly, what kind of math branches they teach, what they don't teach? That's another thing. Yes, actually, there are something they don't actually teach, but it's for example, logic. They usually don't teach that. And graph theory, by the way, also they don't usually teach that if you are a math major. well, yeah, I'm digressing because that's a. Let me just cover a little bit. So anyway, so first of all, there are, what branches of math are there? That's one thing. You have algebra, you have um, geometry, you have discrete math. Then the other thing is what courses do colleges actually teach? That's another thing. By the way, the kind of subject they teach, it comes and go. It's like a fashion and fad. Like in this decade, some topic is hot. In like today in programming, for example, machine learning is hot. Everyone is like machine learning. Every university will like, oh, we teach machine learning. But then next decade is something else. So what university teach is another thing. We're gonna talk about that. So in general, graph theory. If you are a math major, also of course depends on what is your subject of study. What's your intended specialty? For example, if you are a programmer, computer science student, you will likely learn graph theory in your undergraduate degree. Now, if you are a math major, you may not, you may not have taken graph theory. But however, here's what I want to say: group theory. If you are a math major, group theory is absolutely a must. It's a must. It's like the first dish. Okay, so I'm trying to give you a sense. What are the differences between the different subject of math in terms of what they teach in university for undergraduate. So Daniel Anglo says textbooks are expensive, but open source is free. Yeah, yes, very. I have also I have a collection of free open source math textbooks. So I talked about this in a few months ago in my video. So you can, all these are free. I collected and I verified, they are solid. They are quality material. They are almost, every one of them is written by professors. Either I have read them, mostly I have not read them, but I have verified, the professor, the content is solid. So you can check out my collection of math textbooks. These are free. For example, this is calculus. I'm going to talk about these. Like I'm going to talk about what they teach in college. So anyway, so this you have number theory, probability, calculus, linear algebra, real analysis, complex analysis. So let's go back to some of the great books on math. So I'm talking graph theory, group theory, and this one complex analysis. This is also a great book. Now let me go back. So I have 3 books here. Now this graph theory book and this group and their graph, they are introduction to the subjects, to the graph theory and to group theory. They are written such that for non-professional, like for if you don't know anything about math, you don't know calculus, you don't know anything about programming, these 2 books are fantastic. They are good. So they serve as an introduction. Once you read them, after you read them, they are thin, very thin. After you read them, you can just go to Wikipedia and you can you have sense what to look for. You can actually go on and actually obtain a PhD level. You can, well, undergraduate level of graph theory or group theory by reading Wikipedia and links from it. Actually, yeah, it's possible today because info is all online. So anyway, these 2 books are introductory. Now but however, those 2 books are not in depth. I mean, if you are, for example, if you are, they are great intro, okay, but if you are in Stanford University, for example, you are taking half a year to study graph theory, then this book is not enough. They can serve as the first 2 months, for example. Same thing with this book. First, 2 month course, 2 hours a week, they work, but not for the full, half a year. But this book, visual complex analysis, that's a full, in-depth, rather, to great extent, course textbook. It's a full textbook on complex analysis, and it does require you have to know calculus. Okay, you must know calculus, and you must know, let's say, some linear algebra. Well, calculus is necessary at least. So this is a full, textbook. I have it here. It's a fantastic, book. So Danielle says a question: what is not a ripoff? Like cable television, for example. What is not a ripoff? What do you mean? What is not a ripoff with respect to, like, anything? Um, yeah. So what is the context? So anyway, this is a great book. This requires, calculus. You must know calculus. So anyway, that's textbooks. And then let's talk about this. So I have some pretty mathematics, pretty math, collection I have here. So this, 19 Chinese knots and braid theory. When you have weaving like that, they are extremely, for example, this one, this, how do you call this, yarn or a sweater? How do you, like, if you have a sweater like this, how do you call that? How do you guys call that? So, but look at the patterns. They are extremely complex, and, so they are like, in order to have this pattern, it's like a pattern within pattern. For example, on the whole, you see, they are like braids, like hair braids, but each one is actually also braided. And the question is, how do you make these? How do you even begin to make these? Cable night. Oh, okay. So that's called cable night. So this is, like, so to the, you guys math oriented people, nerds, so this is just amazing. And mathematicians have studied this, though. And, I've seen papers. I have papers, actually, a mathematician. I asked him to send me. And also look at these. Let's have a look. This, this, you can see this kind of thing. It's very common, in China or Taiwan. I don't know if in USA it's in common. And how do you call this? So, look at this tablecloth. So these intricate patterns. Uh, it'd be something to, like, you have to design it. Like, you have to think about how to design it, then you have to knight it. So, it's like a human artifact. It's just amazing. So you have these kind of things. These are, weaving and, braid theory, and, in China, Chinese has this traditional decorative thing called Chinese knots. That's interesting. Oh, and then you have this basket weaving. Yeah, this is also, so it's, the proper word is wicker work, wicker works. Yeah, this, they are like made of rattan. Like, you see them in chair. They are, these things are very cool. When in summer, it's very, cool to sit down. This one is no good. It doesn't look very good. But anyway, because it doesn't illustrate the intricate math patterns. But let me show you some of, wait, let me show you some of the rattans. Okay, so let me see. Let me show you Sally. Um, the House of Flying Daggers. there. Okay, there I have a photo of a girl with this hat, weaved hat, and yeah. Okay, so this is not so great. You see the pattern. They make this hat, and you have to weave it. Bamboo or rattan or whatever. But this one, it doesn't seem it's too regular. But it must have a hexagonal pattern to it. But there are many. Let's see if we can find some beautiful ones. So how long have I been talking? 35 minutes. 6 people watching. Hi guys, say hi. Okay, post comments, opinions. Just post it. Okay, so these are good. You see, when you do kind of searches like this, the key thing is the right word. You want to find the right word. Once you have the right word, you'll find what you want. So let's see, WICKER, wicker work. Let's say wicker hat. Okay, we're getting close. So we have this one. Okay, it's still irregular though. Let's see. I want to find one that's very regular and oh, then we got this beanie beans. How do you call this beanie? Yeah, I think beanie caps. That's not well. Anyway, so you see these intricate patterns. Anyway, that's not what I'm trying to find. But anyway, let's go back to um, so yeah, so 19 patterns. So these are interesting, uh, and Wikipedia has article on that great theory. Um, then we have projections. All these lamps, fascinating lamps, beautiful projections, and you have this Klein bottle opener. She made it. She this girl, this woman, uh, Bath Sheba. She makes this. You can buy it. Anyway, so this page is about interesting things. Oh, the thing interesting about this, I categorize them into the proper math area they are studied under. So this kind of thing is, not theory or braid theory, or I don't know if there's a term for weaving theory. Uh, so and this one is spectacular. This hyperbolic geometry, this lamp. You can see this lamp. Let me open. You see, so someone 3D printed this thing. This this lamp. You can see it's actually it's called hyperbolic surface. Hyperbolic surface is such it's a manifold. Hyperbolic space is such that and uh, I think any two lines will meet each other in in one way or multiple ways. I forgot. Anyway, so it's actually more than that. But anyway, hyperbolic geometry. It's so you have this is this so we call them models of hyperbolic geometry. This one is a hyperbolic surface, and it's such that it's very flamboyant. It's like it wavy, it grows, and it gets more wavy and more wavy as it grows. uh, so it's a model of hyperbolic geometry. You study these kind of things in when you study hyperbolic geometry. Then these are projections. They are you study them in under projective geometry. But then you have this stereographic projection. There's a video. It's very good by this guy, Henry Seligman. Henry Seligman.
Stereographic projection. So stereographic projection is a map from the sphere to the plane. And the way that it works is you look at the north pole of the sphere and you draw straight lines. Which line hits the plane? Where does where the line hits the plane? Being in the dark, well, by which is a pretty good approximation to a point light source. And if you arrange,
So he made this 3D model. It's fantastic. It's a stereographic projection. So stereographic projection is, when you shine a light on top of a sphere and project whatever patterns to from the sphere to a plane. This is called stereographic projection. And just like this. And it's a model. And in math, this sphere is called Riemann sphere. And it's a model for the complex plane. So the whole thing, the math of this subject is complex analysis. Uh, so that's what this is about, complex analysis, which is that book was about, we showed before. And you have this Klein bottle, it's under topology. Then you have these tilings and patterns, and then you have this roller coaster, which I classify it under calculus. This is most typical of calculus. You want to study the speed, the inertia, the kinetic energy and things like that when you build a roller coaster. If you make then you have to do derivatives and integration. So what happens if you made a mistake in derivative? The consequence is death. So calculus, roller coaster. Then from linguistic point of view, it's roller coaster. It's interesting because in the old days, how this works is that you just you pull a bunch of seeds high, then you just drop it and let it glide, let it coast. So that's called roller coaster. But in modern ones, you don't coast. They are driven. They are powered. You are driven into sinuousness. So that's a roller coaster. That's calculus. So why? So then you have this water curtain. This is a photo of a fountain. Some I think he's a mathematician. He took a photo and he actually analyzed why this pattern happens. If you go to his Twitter, he does some explanation on why it happens. It takes a while to load. But anyway, so yeah. So you can see, so, and this I categorize it into chaos theory. So this is actually chaos theory. This there are many ways to categorize this photo. Like you can put it into you can put it into cellular automata, or you can put it into dynamical systems. So what is they are kind of all related. Dynamical. Let me explain what is dynamical systems. Dynamical systems, you can search Wikipedia. So dynamical systems is a branch of math. What is it about? It's when you have a function, of one variable, you put in a number and another number comes out. Then you take that output, feed it back to the function, and another number come out, and you repeat. You do a recursion. So in programming, this is called recursion. In math, they don't call it recursion. This is called iteration. Okay, so you have a function. You put in a number comes out, and you take that number and feed it back to the function. So by this process, you got a sequence of numbers. This process, it's called iteration in math. In programming, we call it recursion. So in this iteration, you got a bunch of numbers. Then what you want to study is that you want to study the properties of this sequence. How, for example, if you recurse a function, what will happen? For example, let's say the function takes a point as input, a point in the plane. Then it comes out, so another point somewhere else in the plane. So if you plot the sequence, what will happen? Will they like repeat? Will they become a loop, or will they, like behave? How the point? Where does the point move to? So this study is called dynamical systems. Basically, you study the iteration or recursion of a function. Now, when you study this, you'll find many interesting phenomena. Like you'll find sometimes a function will behave in a strange way. Then when you focus on that particular property, that is called chaos theory. That is what chaos theory is about. Because when you study a function iteration recursive function, you will find there are certain interesting behaviors. That's the beginning of chaos theory. So this thing, you can consider the whole thing as dynamical systems, where essentially from in terms of physics, it's molecules. They have forces, they have surface tension, they have grand force. I don't know physics, but you have the intrinsic force between molecule. But anyway, but eventually you get so essentially what pattern, like when you have water drops on window, sometimes which drop will merge with other drops. It's unpredictable. uh, Typically this process are unpredictable, so that's part of the interesting thing mathematicians want to study. So this chaos theory. Then you have polyhedrons. Look at this one. This one is a fun one. Someone made this. Then you have fractals. This one is also a beautiful one, where you can cut paper and make this pattern, fractal pattern. But anyway, this one is from an airport, where you have this beautiful octahedron structure. Let's see. Yeah, so let me read the comments. So group theory is fascinating. Linear algebra is fascinating. Come to think of it, calculus is quite fascinating. I think the way it is taught is maybe shameful boring. Yeah, that is true. Like when you read math, actually in general, when you read, this is true for a lot of things. When you read, like for example, I read math. I look at lots of math textbooks, or sometimes even non-textbooks, math books, and or I read online many of these math topics. They will say, "Oh, group theory is one of the most important in math." Then you read calculus, then you'll say, "Oh, it's the most important in math." Then you read complex analysis. You'll say, "Oh, this is the most important in math." Like when you don't know the subject matter, like when you are a beginner, you try to read what they are on Wikipedia. You tend to see that it's almost like every subject they will say this is the most important, or sometimes they'll say this is the most elegant math. Group theory or graph theory, or actually for complex analysis and group theory, sometimes you'll see that, or um, this is the most beautiful math. But the point is, like, if you don't know the subject, you tend to like almost like every subject is the most important, but just exactly which is the most important, you don't know. similarly, but by the way, this applies to movies as well. Like if you look at movies, so they'll say, "Oh, this movie is the first to won, this award. This is the first to feature, you know, something something. It's like then another movie. This is the one of the greatest movie because it's this or that. After you read a few, you get confused. It's like every movie is the first this or that. So just exactly which one is actually great. One way to find out is actually to have a rank. Instead of this is the first this or that, because everything can be first. Like Xah Li is the first to this is the first person to be named Xah Li. So the first doesn't matter anymore. Like everything is first. Everything is the first of something. So instead, you want a ranking. Now, so if a movie says this movie is considered to be the top 10 in the decade, then you have some sense how important or how great it is. In a similar way, math, when they say this is important, you have like group theory is very important, complex analysis is very important, graph theory is very important. They are all like fundamental. But then if you say, okay, if you have a rank, or like between, comparatively speaking, which of these is more important, then group theory, I can tell, for example, group theory is more important. uh, Complex analysis and graph theory, they are like they are secondary, depend like. Okay, then between complex analysis and between graph theory, which one is more fundamental? That depends. Like that depends on what's your field, what's your concern, what's your study. For example, if you're let's say if you are a physicist, then complex analysis is absolutely more fundamental than graph theory. But if you are a computer programmer, if you are a programmer, graph theory is far more important. You don't do anything with complex analysis, you see. So that's how. But however, but if you are a math major in general, if you intend to be a mathematician, group theory is the more fundamental. Then complex analysis is more fundamental, because graph theory, they are not the main dish of math. But anyway, so let's move on to the other subject. So let's look at just exactly what a math major study in a university. So here I have the courses I try to verify. So what university actually teach for a undergraduate math. So I actually went to a Stanford University website. So I get a list. So anyway, so let's see what. Okay, so I get a list. So you can check out the list. You can check out, but basically I can tell you what it is. So if you are a math, well, first of all, it depends on what major you are. If you are a physics major, if you are engineering major, if you are chemistry, uh, you don't take your math. The math you are required to take is typically calculus and multivariable calculus. Now, if you are a computer science major, then you also typically need basic calculus and maybe graph theory uh, and linear algebra. Okay, but anyway, but if you are a math major, you are a true math major, you intend to focus on math typically. So in a university, typically 4 years. The first year you need to take calculus, basically introduction to calculus, everything. And yeah, that's almost enough for you. Calculus and maybe some statistics. Okay. In the second year, you might, and calculus and multivariable calculus, basically calculus with multiple variables, including calculus subdivide to differential calculus, integral calculus, then analytic geometry and multivariable calculus. That's the thing. And before that, you take pre-calculus and intro to analytic geometry and trigonometry. That's kind of like high school. So first year of college, calculus and multivariable calculus. Second year is usually introduction to linear algebra and introduction to differential equations and yeah, linear algebra, differential equations, and maybe statistics. Like different university, they the course varies. They varies, but basically that's it. The third year for a math major, that's usually the beginning of real math major. So the third year is typically the two most important are abstract algebra uh, and analysis. Okay, that's the two main thing. Abstract algebra, which includes group theory, field theory, ring theory, a combination thereof. That's abstract algebra. That is the most important abstract algebra for a math major in third year of university study. And equal importance to that is what's called analysis. Analysis is basically calculus, but in a mathematician's way. So you have abstract algebra and analysis. This is the third year study for a math major. Now for the fourth year of math major study, it can be quite a few things. Usually, okay, you can take graph theory. Graph theory you can take in third year. It's independent. You can take it's actually you can study first year of university. So like I said before, they are not the main thing in math for math major. So for example, there's also combinatorics. Now combinatorics, graph theory, group theory, they are all kind of related, but they are all independent. They belong to discrete math. They are not the main dish of math majors, mathematicians. They are like, you computer scientists go study that. They are not considered. Usually, they are, in a sense, they are treated as like that real, not real math. Like computer science. They are actually, I mean, they are real math, but they are not the main thing for mathematicians. So so in the fourth year, you study differential geometry, topology, analysis on manifolds. That's like differential geometry. Yeah, that's basically differential geometry, and differential topology, algebraic topology, which is basically algebra, more advanced, elementary of theory of numbers. Now, okay, theory of numbers again. That's not that's not the main dish, kind of. Anyway, so you have set numbers. Yeah, I mean, there are so many ways. And economics, mechanics, they are not main dish of math. And light and heat, and theory of probability. Again, probability is not main dish. The main dish is about analysis and algebra and anything that's sub branch out of it. Analysis, algebra, topology. That are the main things of for mathematicians. Then sub branch, they have differential geometry, differential algebra, algebraic topology. Not well, differential geometry. There's no such thing as differential algebra. I don't think. Maybe there is. So anyway, differential geometry from analysis, differential topology, algebraic topology, uh, you know, um, things like that. That's basically fourth year of graduate courses. So that's kind of introduction. That's kind of introduction to math courses. So I think that's it for today. That's what I'm gonna talk about. Um, yeah, some interesting math topics. What do you study? Uh, so any comments, questions, opinions? I'm kind of tired and I'm going to go to sleep. Any comments? Sean, Danielle. Okay, that's it for today. Thank you guys for watching. I hope to see you next time. Bye. Bye.